All right, now to sketch rational functions, we just have a couple of different things, right? Like now we're going to be looking at the asymptotes, right, that are formed and how to incorporate that. So let's start on this one. So f of x is equal to x squared minus 2x plus 1 over x. So the domain of this one, so the domain, we just have to look at the restrictions on the bottom, right? So we'd say x cannot equal, well, 0. And then you could also say where x is a member of the real numbers. All right, now intercepts. So let's see for the the x-intercept. So x-intercept is going to be where y is equal to 0. So we'll say 0 is equal to x squared minus 2x plus 1 over x. And we'll just remember that, it doesn't actually matter about the denominator, right? I'm only really looking at the numerator, because if the numerator is 0, then the whole thing is 0. So in this case, so I'll say 0 is equal to, and I'm just going to look at the top, and I'm also just going to factor it. So that would be the same thing as x minus 1 times x minus 1. So the x-intercept would happen at x is equal to 1. Right? Now the y-intercept. So the y-intercept is going to happen when x is equal to 0. But right off the bat, I kind of see there's a problem here. I can't throw 0 in for x, or I'm going to be dividing by 0, right? This is a situation where the y-intercept does not exist. All right, so symmetry. So for symmetry, we're going to be plugging in f of negative x in and seeing what we get. So let's do that. So plugging negative x into all of these, we get negative x squared minus 2 times negative x plus 1 over negative x. So this would be the same thing as, well, squaring that negative would be just positive x squared, negative and a negative, and make that plus 2x plus 1 over negative x. So that is neither. Because the other one I could do here, right? You could, take this negative that's sitting on the bottom, right? Because that would actually be the same thing as just having like negative sitting out front of the whole thing, really. Like you could take that negative and just stick it out front. Like that is the same thing, right? Like if these were in brackets, hopefully you can kind of see that. So negative, and then all of this. So x squared plus 2x plus 1 over x. You can see that this is also not f of x either, right? So we don't have odd symmetry either. Okay? So, okay. So neither. So it doesn't have, so it has no symmetry. Okay, asymptotes. So our asymptotes here are going to be at, well, we have a vertical asymptote at x is equal to 0, right? That's where we're dividing by 0. So let's figure out the limit, like figure out what's happening now at that vertical asymptote. Like, is it going to positive infinity or negative infinity? So I'll take the limit. I'm going to take the limit as x approaches 0, and I'll do from the right first, of x squared minus 2x plus 1 over x. Okay, so now as x approaches 0 from the right, so I'm thinking a number like 0.1, right? Very, very small, like way smaller than that, but it's good to get your mind wrapped around it. Now imagine what happens as that gets very, very small. This becomes very, very small, right? This term becomes almost 0, pretty much 0, right? So that's 0 minus pretty much 0. So I've really just got positive 1 in the end there. So in the end, that thing's coming out positive, right? Not x, positive. Over, and in the bottom, well, yeah, this is becoming ever and ever closer to 0, which is really why this is going to be infinity, right? Because we're dividing by 0. But it's going to be like close to positive 0, right? It's still going to be a positive number. So that's positive over positive. So this thing is going to be approaching positive infinity from that side. Now if I take the limit as x approaches 0 from the left of x squared minus 2x plus 1 over x. Now the top really looks the same, right? Because we've got, well, like negative pretty much 0 minus negative pretty much 0. Both of those didn't really matter. I'm just looking at the 1 here. So this would be positive. But now on the bottom, this is approaching 0, but it's still negative the whole time. So this is going to be divided by a negative. Yeah, so it becomes negative. So this would be approaching negative infinity. So now let's look at our horizontal asymptotes. So HA. So if we take the limit as x approaches, and I'll just do positive n minus infinity together, of x squared minus 2x plus 1 over x, then we have a situation where the degree of the top is bigger than the degree of the bottom, right? This one's the top is growing faster than the bottom is, so this thing never does approach like 0 or 1 or any kind of like number, right? So in this case, does not exist. So if it doesn't have a horizontal asymptote, we've now learned though that it could still have a slant asymptote. So let's figure that one out. So for a slant asymptote, the way we do it is we actually just divide it, right? We'll divide the top polynomial by the bottom. So we'd write that as, so x squared minus 2x plus 1, and then x. So we'll say how many times does x go into x squared? So it goes in x times. X times x is x squared. And then we subtract. Oh, so it becomes 0. Bring down the negative 2x. How many times does x go into negative 2x? Well, it goes in negative 2 times. And you can pretty much stop there, but we'll finish it. So negative 2 times x is negative 2x. And then we'll subtract that, so that becomes 0. And now we know we got a remainder of positive 1. And really, positive 1 over x, right? Because it never went into x. But, but that's okay. The thing we really needed here was this, right? That is what our slant asymptote is. So we have a slant asymptote at y is equal to x minus 2. So that'll be helpful when we're sketching this guy. All right. Increase and decrease. So let's write out the original function again. I'm going to show you guys a shortcut. So f of x is equal to x squared minus 2x plus 1 all over x. Okay, it's bothering me. Okay. All right, so what we're going to do for areas of increase and decrease, just like in the last video there, we're figuring out where the derivative is going to be equal to 0, right? Because that's going to be where it's switching from increase to decrease at any point, right? So we want to find the derivative of this. Well, we could do the quotient rule, right? We could do that, you know, that'd be fine. Get a little bit messy. We could also rewrite this as, you know, x squared minus 2x plus 1 times x to the negative 1 and make it the quotient or the product rule. But the other thing we could do is just rewrite this right off the bat, right? This is the same thing as x squared over x minus 2x over x plus 1 over x, right? Just they're all over x. So then this would be the same thing as just x, right? X squared divided by x is just x minus 2. And then in this case, this would just be 1 over x, so plus x to the negative 1. And now that will be so easy to take the derivative of, right? So if you can get away with it, I would do that. So let's say the second derivative of this, so this would just be 1 minus, so then, yeah, minus 0, but won't worry about that. And then the last one would just be minus minus x, and then to the power of negative 2. Let's take the derivative of that one. Okay, so then rewriting this a little different. This is 1 over x squared, which would be the same thing if I, x squared and x squared on the top there, right? This would be the same thing as x squared minus 1 over x squared. So I said 1, but I wrote an x apparently. There you go. Okay, so now we want to figure out where this is equal to 0, right? So where is this equal to 0? So I'm really looking at the top here. So this would be, I'm going to write just the numerator. So x minus 1, x plus 1. So this is going to be when x is equal to plus or minus 1. And then, yeah, sorry, I said I'm only looking at the top. Maybe I cut myself off a little bit there. You really should look at that one too, right? Because that'd be a change in my areas of increase and decrease, right? So, but when I'm looking for my my max, my min, I won't really need it. So yeah. So sorry, this is a critical number, and then we would also have, because of the dividing by 0, we'd also say one of the critical numbers would be x is equal to 0, right? Because that really is our asymptote. So that could be a place where, if you've got your graph where that's your asymptote, maybe it's concave, or it's increasing here, and maybe it's decreasing there, right? So that could be a switch. All right, so let's make a chart or a number line. All right, so we'll put down our critical numbers. So that would be 0, and then -1 and 1. So we're figuring out our areas of increase and decrease, right? So we want to do this for the derivative, right? So let's write that above so we can see it. So the derivative, so f prime of x was equal to x squared minus 1 over x squared. All right, so if we throw in a number like -2, right? So over here is what I'm looking at. So my f prime of x. So yeah, like -2. So if I threw -2 into here, that'd be -2 squared, right? So that's gonna be like something like 4 minus 1. So this thing's coming out positive on the top, right, or in the numerator. And then in the denominator, -2. So I'm squaring it. It doesn't really matter. This is coming out positive as well. So this section is going to be positive. So the derivative of f is positive, which means the original function would be increasing, right? So it's increasing on that interval. Okay, on the next interval, so we've got something like -0.5. So if I threw -0.5 into this, right, then that's going to be, well, it's coming out positive anyway because I'm squaring it. And then it's a small number. 0.5 squared makes it an even smaller number, right? And then -1, this thing's definitely coming out negative on the top. And then on the bottom, this is going to be positive again because I'm squaring it. So then this would be negative. Okay, so this thing's decreasing on this interval. And then from 0 to 1, it's going to be similar to above, isn't it? Because I've got, doesn't really matter at all that it's going to be a positive 0.5 because it's coming out negative, right? For the same reason as last time. And then in the bottom, this will be coming out positive. So again, we're going to be decreasing. Okay, and then if I threw like 2 in here, then this would be kind of the same as our original side over here. 2 squared is going to be like 4, so it's positive on the top. And on the bottom is going to be positive as well. So this is coming out positive. All right, so let's quickly write our intervals of increase and decrease. So it will increase from the interval -infinity to -1, unioned with, and then over here, 1 comma infinity. It will decrease from -1 to 0, and then unioned with 0 to 1. Okay, now for the next part, for max and min, it's pretty clear where our max and our min are from this picture that we've made up here, right? So we have a max at -1 and a min at 1. Right, this is where they're coming together. And this makes sense that we don't have anything at 0, right? And even if they were, let's say, going the same direction, it still wouldn't be a max or a min, right? Because that's our asymptote, right? That's not going to be a max or a min. So the 0 doesn't really come into play there, right? So, all right. So we're going to have a max at, and I'm going to put in f of -1, just the original function, which is equal to 4. So that point would be the point -1, 4. Okay, and you're going to have a min at f of 1, which is equal to 0. So at the point 1, 0. And these are yeah, local mins, right? So okay, so now for concavity, we're going to be needing to figure out the second derivative, right? So here, before I write that down, let's go back up and get the first derivative, right? So I could, you know, take it from here, right, and do the same thing. But if you remember, this was also the first derivative, right? That's already kind of like in the best form for us to figure out the third derivative, right? So let's take this one. Let's write that one down first. So that would be, so we'll remind ourselves that f prime of x was equal to 1 minus x to the -2. Now that's easy to take the derivative of, right? I don't got to do quotient rule, product rule, nothing, right? Just take the derivative. So f double prime of x is going to be equal to 2x to the power of -3, or 2 over x to the 3. All right, so set this equal to 0, and okay, so you'll probably figure out this doesn't seem to be working, does it? I can't really solve for x in this case, right? I can't really do anything. So there is no, this is actually telling us something. This is telling us that there is no inflection point on this graph, right? But especially with these rational functions, there's an asymptote, right? So there could be like a case where you've got concave up on one side, concave down on the other, right? So we still will have areas of concave up and concave down, or intervals. So we're going to be looking at still our critical numbers, but we're looking at this one, right? So x is equal to 0 is a critical number. Okay, so what we're going to do there then, we'll make our table. I keep saying table, but I mean number line. And we'll set it equal to 0. So we'll look on the left of that, and we'll look on the right of that. So if I threw -1 into the derivative here, so this would be, so whoop, come on, there you go. F double prime of x in this interval is going to be negative. Right? So you got -1 into that, or anything more, it's going to be negative. So that means our f of x would be concave down. Concave down on this side, right? And then on the right side, if you threw in, let's say, a test point of 1, then this is going to be positive on this side. So that means it's going to be concave up on this side. Okay? So even though 0 isn't an inflection point, it'll still change which way it's concave up and which way it's concave down. So, all right. So that's it. So point of inflection, I already kind of went over that. It does not exist. All right, we're ready to sketch this guy. So let's go back to the beginning. Let's figure out what we knew. X-intercepts are always an easy way to start. So intercepts, we knew that there was going to be at 1, and then there was no y-intercept. Okay. So we know it's going to cross at 1. And there is no y-intercept. And we also knew that this thing had a vertical asymptote, right? We also knew that at x is equal to 0, we have a line going there. So that was happening. Now, the other one that's going to be interesting for us will be this one, right? Our slant asymptote. Y is equal to x minus 2. So I'm just going to write that to remind myself. We have a slant asymptote at y is equal to x minus 2. Okay, so let's sketch that one. So that's going to be from -2 and then going up like so. So something like that, right? Okay, what else do we know? Well, we know there's no inflection point. We know that it's going to be concave down on the left side of 0, right? Okay, so we also should look at our minimum and our maximum, right? So we know that we have a maximum at -4 or -1 comma 4. So -1 comma, what was it? -1 comma 4. All right, so I'm seeing a mistake I made. I think I just wrote it down wrong. Sorry, guys. This was -4. -1, -4. So if we go back here, that makes more sense. We're going to be at -1, -4. All right, so it's going to be a point there. And then we had a minimum at 1, 0. Whoop. So at 1, 0, well, that was the same as our x-intercept. Okay, so that must be a place where the graph just bounces off the x-axis, right? And then I think we got enough to sketch this thing because it's going to be concave down from this side. It's going to have a max there and then come back down. And then same idea on this side. So it'll be approaching this asymptote, dipping down, just touching the x-axis there, and then off along the slant asymptote. And there you go. We've sketched it.